Hello, this is the fourth video in the third series for OCR AS Core Pure Further Mathematics. In this session we will explore the link between determinants and transformations. So, looking at matrices and transformations, we have seen this example in previous sessions where we start with the unit square and multiply by this matrix. Multiplying by the matrix 1021 results in a transformation of the unit square with a shear with the x-axis invariant. You can see that the point 01 is transformed to the point 21. Here the area of the transformed shape is the same as the original square. Remembering that the area of a parallelogram is base times perpendicular height, well, you can check this for yourselves. Here is another example of a transformation, where the orange square is an enlargement of the black square by a scale factor of 2. In other words, the lengths of the sides have doubled. If you look at the area of the object, it's 9 squares, but the area of the image is 36 squares, which would indicate an area scale factor of 4. The transformation performed can be described by the following matrix T equals 2, 0, 0, 2. So an enlargement of scale factor 2 in a linear sense has an effect of an area scale factor change of factor 4. You may wish to pause the video here and try different enlargements to see if you can spot the pattern or relationship. Here is another example of a transformation of a unit square under matrix A, 3 minus 1, 1, 1. You can see that the image is 0, 0, 3 minus 1, 4, 0, 1, 1. This is shown as in outline by the parallelogram with red sides. The area of a parallelogram image might be seen to be 8 squares of rectangle. Take away 2 times small 0.5 square triangles. Take away 2 times 1.5 square triangles. If you look at the whole outline shape and then take away the pieces around the edge, this would give us an overall area for the parallelogram of 4 units. Might be worth noting that the determinant of A is in this case 3 times 1 minus 1, which would give us 4. Obviously the area of the unit square, or the original object, was 1. Therefore, the area of the image is 4 times that of the area of the original object, and that happens to be the same as the determinant of the matrix used for the transformation. In fact, when you try a number of examples, you will see that for the transformation of a unit square under any matrix M, A, B, C, D, you will get the image 0, 0, AC, A plus B, C plus D, B, D. And the area of the resulting parallelogram image may be found to be AD minus BC, or in other words, the determinant of that matrix. For 2 by 2 matrices M, the associated image area will be changed by a scale factor of det M. Well, what about successive transformations? If we had a transformation represented by matrix A, followed by the transformation represented by matrix B, where A is 1, 0, 0, minus 1, and some of you may recognize this as a reflection in the x-axis, and B is 0, 1, minus 1, 0, which is a 90-degree rotation anti-clockwise about the origin, then we'll see how this works on the red object. So, firstly A, being reflected in the x-axis, would give us points here, here, and here. So in other words, this shape here. So that's after A. And then if you note, if you're rotating around the origin by 90 degrees, you would indeed end up with this pink image after the double transformation. Or in other words, BA. Remembering that you would multiply firstly by A, closest to the shape, and then secondly by B. So BA gives the combined transformation. If we were to look for the inverse of BA to map back from the pink image to the original red object, what would we do geometrically? Well, we would undo the rotation first and then undo the reflection. You will remember a previous result that the inverse of BA will be a to the minus 1, b to the minus 1. So in other words, you would undo b first and then undo a afterwards. So the determinant of a 2 by 2 matrix gives the signed area scale factor of the associated transformation. Area cannot be negative, however the sign of a determinant is geometrically significant. Let's consider the transformations we have represented in previous sessions using 2 by 2 matrices. We looked at rotations, reflections, and enlargements. In a moment I'm going to switch to the dynamic GeoGebra, and we can look at which of these, out of rotations, reflections, enlargements, the order of the inverses or the orientation of the shape are reversed under transformation. Here you can see we have matrix M equal to 0, minus 1, 1, 0, which represents a rotation clockwise of 90 degrees. You can see that the determinant is 1. As you can see, the order A, B, C, D is the same as the order of image A', B', C', C'. If we consider a rotation of 180 degrees, again the determinant is positive, plus 1, and the order A, B, C, D is the same orientation as A', B', C', D'. You should try this GeoGebra program and a number of other rotations to convince yourselves, but you will find that the determinant is always positive and that the orientation of the vertices is not altered under rotations. Here we are looking at a reflection in the y-axis. And you can see that where we have A, B, C, D going round clockwise, A', B', C', D' goes round anti-clockwise, so the order has been reversed. And indeed the determinant is minus 1. For a reflection in the line y equals minus x, again the determinant is minus 1, and the orientation has been reversed. Here is an enlargement of scale factor 3, shown by m equals 3003. The determinant is positive, 9. We had a unit square object. The image is 9 times bigger, and you will also notice that the orientation of the original vertices remains unchanged. Therefore, if we consider the determinants for following matrices, 1, 0, 0, minus 1, or reflection in the x-axis, we know that that is minus 1, and that there will be reverse orientation. For 3, 0, 0, 3, enlargement scale factor 3, centre origin, we know that the determinant is 9, and that the orientation will remain the same. For 0, 1, minus 1, 0, which is an anti-clockwise rotation of 90 degrees about the origin, again we have a positive determinant, and therefore the orientation remains the same. So overall our conclusions are that when you have a negative determinant, you will have a reverse orientation to a transformed object. The determinant of a 2 by 2 matrix gives the signed area scale factor of the associated transformation of a 2D shape. Let's moving on, the determinant of a 3 by 3 matrix will give the signed volume scale factor of a 3D shape, for example a unit cube being transformed to parallelepiped. The sign of determinant is still of geometric significance, as the 3D shape vertices orientation is preserved if the determinant is positive, and reversed if the determinant is negative. If the determinant of a matrix is 0, for example the matrix 1, 4, 2, 8, then under this transformation all points on the plane will be mapped to a straight line passing through the origin, in this case y equals 4x. We'll show this using GeoGebra in a moment. More than one point may map onto the same image point, and this is called transforming the plane. Now, a special case is the 0 matrix that maps all points to the origin. And here's the GeoGebra program we'll be using. You may have noticed that for the matrix 1, 4, 2, 8, the second column was a multiple of the first column. In this example here, minus 1, 1, minus 2, 2, again you have the second column being a multiple of the first column, and the unit square has been transforming the plane to a line, in this case y equals minus x. You will notice that the determinant is 0, thus indicating that M is a singular matrix. So, for a 2 by 2 matrix with determinant of 0, any shape is transformed into a shape with 0 area. In effect, then, all points on a plane are mapped to a straight line passing through the origin. For a 3 by 3 matrix with determinant of 0, any shape is transformed into a shape with no volume. So, in effect, all points are mapped to the same plane, and the unit cube would be mapped to a parallelepiped of volume 0. In the next session, we will look at the link between inverses and transformations.